Dear students, we have started the topic applications of derivatives. Now in this lecture we will further extend that topic to study some new things. So here we are, and that new thing is actually the absolute and local extrema of a function. What is absolute extrema of a function and what is local extrema of a function? Let us try to understand the difference between these two. So the difference between local and absolute extrema is shown here in this figure. We see here that this is the graph of a function y is equal to f of x, and the domain for that graph is taken to be a and b. And we have plotted this graph between a and b, including a and b. For x equal to a, this is the value of the function f of a. This is x and this is f, this is c, and that is f of c. This is, for example, e, so that is f of e. This is d, so that is f of d, and this is b, so that is f of b. In this graph we see that there are three minimum distances. If you see here, this is the minimum distance, that one and that one. Among these three minimum distances, this is the smallest distance among these three distances. So we say that this is the absolute minimum value of the function. Absolute, the smallest functional value is called the absolute minimum value, and the rest of the small distances, smaller values, this value and this value of the function, these are called local minimum values of the function. Absolute means throughout these distances, this distance is the smallest one, so this is absolute, and the rest of the minimum distances are called local minimum values of the function. Similarly here, there are maximum values. For example, at x equal to z, f of c is maxima, and for x equal to d, f of d is maxima. Between these two maximum values of function, this distance, this value of the function is the maximum value. So this maximum value is called absolute maximum value, and the rest of the maximum values or value is called local maximum value of the function. This absolute maximum value can also be taken in the sense of local maximum value, and this absolute minimum value can also be taken in the sense of local minimum value. So we may say that absolute minimum or absolute maximum can be taken in the sense of local minimum and maximum value. But that is the difference between absolute and local extremas. Now we are in position to define absolute extrema of a function. Absolute means global. Absolute, you can say absolute or global. Global means throughout in the domain. So global or absolute extrema. Extrema means absolute maximum or minimum value of the function. Maximum and minimum value of a function are combinedly called extremum values. Extrema means maximum and minimum of a function. So absolute means the most extreme value, extreme height, and extreme low value of a function. Let's say f be a function with domain D, and the previous domain we have taken the domain a comma b because the starting value of the function starts from x equal to a, and the end value was considered to be at x equal to b. So let's say f be a function with domain d. Then f has an absolute maximum at c. The maximum value of f at x equal to c is that value of the function, is that f of c, which is greater than the rest of the values of the function. The maximum value, the absolute maximum value of function at x equal to c is that function value, is that f of c. So that f of c will be greater than the rest of the values of the function. All values of the function, this value is the greatest value. F of c is greater than or equal to f of x for all values in the domain. Similarly, absolute minimum value of the function at x equal to c is that functional value of f, is that value of the function which is less than or equal to the rest of the values of the function for all values of x. So whenever f of c is greater than f of x for all x, then we say that f of c is the absolute maximum value, and whenever f of c is less than f of x, all f of x, then we say that f of c is the absolute minimum value of the function. But we are talking here for all x in the domain, for all values of x in the domain. Now there is a slight difference between absolute and local. Local is also called relative extrema. So you may say that local extrema and you may say relative extrema of a function means that local maximum or local minimum value of a function. The definition is the same. You see here, the definition is the same, but this result is true for all values of x, and this result is true for all x in some open interval, and this result is true for all x in some open interval containing this c. So for some means nearby this f of c, and for all means throughout in the domain. So that is the main difference between these two extrema. Now in this slide we have studied that absolute extrema of a function can also be a local extrema. So there are some certain tests. The first one is called the first derivative test for local extrema. How could you find the local extrema? Local extrema means local minimum or maximum value of a function. So there are tests. The first one is called first derivative test. Now what is first derivative test? Suppose that c is a critical point of a continuous function f. What is a critical point? We have studied this thing in the previous lecture, that critical point is that point at which we draw a tangent, and that tangent is parallel to the x-axis. So that values of x are called critical values of x, critical values of the function f. So let's say c is a critical point. It means that you need to find the critical point of the function, and f is differentiable. It means that because we are using here first derivative test, so definitely f must be differentiable. Must be differentiable means you are able to find the derivative of that function at every point in some open interval containing this c. Now this statement is very important moving across C from left to right, from left then to right. So we will be taking values from left to right of C and put those values in the given derivative of the function, the obtained derivative of the function. And we will observe these three things. First of all, if f prime changes its value from negative to positive at C, then f has a local minimum. If you put the left value and the function's derivative and the answer is negative, and then put the right value and the function derivative, and if that is positive, then if f prime changes its sign from negative to positive, then we say that f has a local minimum at C. And if f prime changes from positive to negative, from left to right, this is very important, from positive to negative at C, then we say that f has a local maximum at C. And if f prime doesn't change sign at C, that is f prime is positive on both sides of C or negative on both sides of C, then we say that the given function has no local extremum at C. The given function has no maximum or minimum value at this critical point C. So that is the first derivative test. That is the definition of that test. And summary of this first derivative test, that what should we do? What are the main steps to apply the first derivative test? That is explained here. Summary of first derivative test. First of all, you will be given a function y is equal to f of x that will be given to you, and then you need to find the derivative of that function. Whenever you find the derivative of that function, put the first derivative equal to 0 to get the critical values, because we obtain critical values by putting the first derivative of the function to 0. So you'll get critical values of the given function, that is the values of x. So the second step, we will put the derivative of the function to 0, equal to 0, and we will get the values of x. Now thirdly, this step is very important. Take two values from left to right of x. Those values of x which we have obtained from this second step, we will take the value of x and go to the left and to the right of that x and put these two values in the first derivative of the function. So if prime changes its sign from positive to negative, here from positive to negative, then we say that the function has local maximum value at that value of x. And if prime changes its sign from negative to positive, then we say that the function has local minimum value at that x. If no sign change occurs, that is f prime and f prime, if there is no change of sign, then we say that f of x has no local extrema at that critical value of x. So that is the summary of first derivative test. And here is an example to understand the idea of that first derivative test. The example is use first derivative test for local extrema for the following function. You are given a function f of x equal to x cube minus 3x plus 2. This function is given to you and you are asked to find the local extrema of this function. So follow the steps. The function is given to us, that is say equation star or equation 1 or equation 2, whatever. So that is f of x, x cube minus 3x plus 2. Differentiate this function with respect to x. Whenever you differentiate this function, that will become f prime, and the derivative of x cube is 3x square. The derivative of 3x is 3 into 1, and the derivative of 2 is 0. So here we are, f prime x is equal to 3x square minus 3. That is f prime x, 3x square minus 3. That is equation number 1. Now, and the third step, we will find the critical values of the function. How could we find the critical values of the function? We will put the first derivative equal to 0 to get the critical values. So f prime x is equal to 0 means this is f prime, this should be equal to 0, and solve this equation, convert this 3 towards that side. We will be getting 3x square is equal to 3, dividing by 3 to get x square is equal to 1, and taking square root to get x equal to plus minus 1. So plus minus 1 are two critical values of this function. At these two values of x, this function may take the maximum value or minimum value, or maybe not both of those two values. So there are two critical values, x equal to minus 1 and x equal to plus 1. First of all, taking this critical value, x equal to minus 1, we will take two values from left to right of minus 1 as near as possible. What does it mean? It means that minus 1 will be in the center, and the nearest value of towards this left side of minus 1 is minus 1.1. You can take minus 2 as well, but minus 2 is away from this minus 1. Try to take the nearest value towards the left side and the nearest value towards the right side. So towards the left side there is minus 1.1, and towards the right side there is minus 0.9. So we will be taking these values from left to right. First of all, we will consider this left value and put this left value in the first derivative, and then we will put the right value and the function derivative. So first of all, left value, we'll take the left value minus 1.1, and we'll put this value of x in equation number 1 and this first derivative, because we are using first derivative test. So put x equal to minus 1.1 in the first derivative. That will become f prime minus 1.1, and that will become 3 into minus 1.1 whole square minus 3. Simplifying this side, we obtained plus 0.62, that is a positive answer. So f prime is positive on the left side. Now taking the right value, the right side value, x equal to minus 0.9, and put this value in the derivative of the function in equation 1. Whenever you put x equal to minus 0.9, that will become f prime minus 0.9, and that will become 3 into minus 0.9 whole square minus 3. Calculating this difference, we will obtain a negative answer, minus 0.57. So we see that f prime changes its sign from positive to negative, but from left to right. This is very important, from left to right. So f prime changes its sign from positive to negative. So it means that f of x has local maxima at x equal to minus 1, at x equal to minus 1. Now what is that local maxima? For local maximum, we obtained that x equal to minus 1 is assigned for the maximum value of this function. So put x equal to minus 1 and this function to get the maximum value of the function, which is 4. So at x equal to minus 1, this function has local maximum value of 4, and at which point that local maximum value occur? The local maximum point on the curve is x comma f of x. Now x is minus 1 because we are taking here minus 1, and the value of f of x for x equal to minus 1 is 4. So minus 1 comma 4 will be at the top of the function value. So this is the most top point on the curve, local maximum point, local maximum. Similarly, taking the second value of x, which is plus 1, and that is plus 1, we will be taking the left side value and then the right side value of this one. The left sided value, the most nearest value, the nearest value from the on the left side of 1 is 0.9, and the nearest value on right side is 1.1. So we will be taking this 0.9 first. Left value is x equal to 0.9, and put this in the derivative of the function. So whenever we replace x by 0.9 and the derivative of the function, we will be getting a negative answer. And whenever we put x, the right sided value, x equal to 1.1, and the derivative of the function, we obtain a positive answer. So we see here that f prime changes its sign from negative to positive. So it means that f prime changes its sign from negative to positive, f of x has local minima at x equal to 0.9, at x equal to 1, this one. So at x equal to 1, the function has a local minimum value. So what is that local minimum value? For that local minimum value, we will put this x equal to 1 and the given question. So whenever you put x equal to 1 and f of x, we obtain f of 1 equals to 0. So this is the minimum value of the function. F of 1 is equal to 0, and that minimum value of the function occurs at x equal to 1. So local minimum point on the curve is x comma f of x, and x is here 1 and f of x is 0. So 1 comma 0 is the local minimum point of that function. So this is how we apply the first derivative test to check whether a point is associated with the local extrema of a function. Secondly, in this slide we are going to study the second derivative test for local extrema. We have studied the first derivative test to check whether the function has local extrema or not. Now that is the second derivative test, and this test is simple enough as compared to the first derivative test. So that is the definition of the second derivative test. Suppose the second derivative of a function is continuous on any open interval containing x equal to c. We will put f prime c is equal to 0 to find the to find the critical values of the function, and then we will put that critical value and the second derivative. So if the second derivative is negative, then we will say that f has a local maximum at x equal to c. And whenever that critical value is entered in the second derivative and the answer of second derivative is positive, then we will say that f has a local minimum value at x equal to that c. And whenever the second derivative is 0, then we will say that this test will be failed there. Second derivative test will be failed whenever the second derivative of the function is 0. Then we say that the function may have a local maximum or local minimum or neither. So that is the summary of second derivative test. First of all, you will be given a function. A function will be given to you people, and you need to find the first and second derivative of that function, because we will be using second derivative test, so we need the second derivative of the function. The second step is we need to put the first derivative of the function equal to 0 to get the critical values of the function. That is, we will be getting the values of x, which will be the critical values of the given function. Thirdly, we will put these critical values of x, these critical values of the function, the values of x, we will put these values of x and the second derivative, because this is second derivative test. Now put these values of x and the second derivative. If the second derivative is negative here, then the function has local maximum at x, and whenever the second derivative is positive, then we say that the function has local minimum value, and whenever the second derivative becomes 0, then we say that the function may or may not have local extrema. So that is the second derivative test. Let us take an example here. For example, we are asked to use second derivative test for local extrema of the function. That is the same function as considered in the first derivative test, f of x equal to x cubed minus 3x plus 2. Now for this function, we are asked to find the local extrema by using the second derivative test. So follow the steps for second derivative tests. The function is given to us. We need to find the first derivative of this function and again differentiate with respect to x to get the second derivative of this function. The second derivative will be 3 to the 6x and the derivative of 3 is 0. So 6x is the second derivative of this function. Now in order to find the critical values, put the first derivative of the function equal to 0. That is, put 3x square minus 3 equal to 0 and try to solve this equation to get two values of x, which are actually the critical values for the function. So there are two critical values, minus 1 and plus 1. Now using the second derivative test, first of all we will put x equal to minus 1 and the second derivative. So whenever we put x equal to minus 1 and equation number 2 and second derivative, here 6 into x means 6 into minus 1. So the answer is negative. So see here, the second derivative is negative. So from the definition of second derivative, the function has local maxima at x equal to minus 1. Now what is that local maxima? Put x equal to minus 1 in the given equation to get the local maximum value of the function. And the local maximum point is x comma f of x. X is equal to minus 1 and f of x is 4. So that is the local maximum point on the curve. Similarly, take this second value x equal to plus 1 and put this x equal to plus 1 in the second derivative of the function, because we are using second derivative test. So put x equal to 1 in this second derivative. Whenever we put x equal to plus 1, we obtain that f double prime is positive. So whenever the second derivative of the function is positive, then we say that the function has local minima at x equal to 1. Now what is that local minima? Put this x equal to 1 in the given question, in the given function, to get the minimum value of the function 0 at x equal to 1. So local minimum point on the curve is x comma f of x, which is 1 comma 0.